And before introducing, okay, Russell, thank you for finally making it. It wasn't a trivial, but inside it wasn't either expected. So Quantinuum, one of the sponsors of Multicore World, has another speaker aligned, which for personal reason wasn't able to come. So Russell, thank you very much for coming up on so short notice. I mean, New Zealand is not around the corner.
Yeah, so thank you very much for the invitation and also being very patient, as I apparently am really bad at international travel and it took me a long time to get here, and being flexible with moving things around. Um, very happy to talk here, very happy to talk about all of the work from my brilliant colleagues at Quantinuum. This is, of course, not my work, it's really theirs. I just get the opportunity to talk about it. Thank Chris for giving a nice introduction to quantum. I wasn't sure what all he'd get into, so I have a few introductory slides as well. I'll probably go over them. It'll be a little redundant, but I think a little redundancy is probably okay here, and maybe I'll point out slightly different things. Of course, there's a lot to try and wrap your head around here. As far as timing, I know I want to be mindful, and I know we have happy hour drinks, and I'm worried about keeping us from those, but I'll just ramble, and then you guys can leave and get drinks when you're tired of it, I guess. So Chris mentioned the idea of superposition and entanglement, right, is really driving quantum computing, and so I kind of made this analogy to classical computing. You have a two-state system, right? A transistor, which is either on or off, right? Those are the two states, corresponding to logical 0, logical 1, and you have n number of bits in your system. You can have 2 to the n possible values, but at any given time, you have a single value that you are holding. And then on the quantum side, because of this idea of superposition and entanglement, it's quite a bit different, right? So this thing we call the block sphere, and I was debating whether to show it or not, but I think it tells some story that I'll get into a little bit, to both tell you something about the power of quantum computing, but also some of the challenges that we have. And so the idea is you have a vector. Your state's kind of described by a vector. If it's pointing straight down, it's, here in the case, it's 1, and straight up 0, or but then you can do this thing where you do a single qubit gate, and it can really allow you to put it in kind of this arbitrary superposition state where you have alpha and beta, and these are complex amplitudes. And there's actually a phase relationship between 0 and 1. And what do we mean by that? How is it kind of physically realized that there's this phase? So the idea is, you put it in an equal superposition of 0 and 1, and it's now the vector's pointing along this equator. But this phase relationship, it actually, accumulates phase and rotates around the equator as you just wait, and it's defined by the energy splitting between these two states, divided by Planck's constant. That gives you the frequency at which this thing rotates, right? And this is the basic concept behind an atomic clock. In the end, you just have you take any two states within an atom, and you have this really well-defined energy splitting, and you have to be very careful not to mess up that energy splitting. But then you just put it in this superposition state, and you basically just count how many times you wrap around 2 pi of phase, and you read out the phase by, you have some oscillating field that's coupling 0 and 1. That's how you create the superposition state. And the phase of that oscillating field, that driving field, it matters compared to the phase of this superposition. And depending on the phase, it'll either rotate up or rotate down or do nothing. And so you basically read out the phase this way by rotating it back and measuring 0 or 1. And this is how humans define a second now, right? It's, you take 2 energy levels and say, I think it used to be a cesium atom. Maybe they've changed it now. I'm not sure. 2 energy levels, and you say 1 second is defined as so many oscillations of this phase, in a cesium atom in these very specific conditions and magnetic field and so forth. But this phase, this phase relationship is important because if you don't track it, then you get decoherence. And this is why we don't really see the world as quantum, even though it is quantum, is because there's constantly decoherence. So if you don't track this phase, you're just going to get random answers in the end. And so this decoherence is really the thorn in the side of quantum computing in a lot of ways. But yeah, this is what's happening in our qubits. Our qubits are essentially atomic clocks, and we have to track their phase the whole time. And then entanglement comes into play, right? So you take 2 qubits, and now you can perform these 2 qubit gates that Chris described, and you can actually create entanglement where the state of one depends on the state of the other, and you can make this famous kind of Bell state where you only can get 0, 0, or 1, 1, right, when you measure. So 0, 0 just means both qubits are in the 0 state, 1, 1 means both qubits are in the 1 state. And you can create this Bell state and actually separate these qubits very, very far apart. And you have kind of this 50-50 probability of measuring 0 or 1, but you can measure them simultaneously such that the delta in that time is small compared to the time it would take light to travel between the 2 qubits. And you always measure 0, 0, or 1, 1, which is, spooky, right? This is, if you hate this, you're not alone. Like Einstein kind of famously hated this. He called this spooky action at a distance. He thought there's no way the universe works this way. But there's data. That's how it works, right? And, for our purposes, the upshot here is now you have these entangled states, and you get to the end sort of state space that your quantum system, in this case, a bunch of qubits, spans, right? And this is the Hilbert space. Sorry, it's not. Okay, and Chris used a slightly different example, 300 qubits, so 100 qubits. All of a sudden, you now have 10 to the 30 complex amplitudes that describes the state you're in. And Omar yesterday was talking about 10 to the 14 parameters, right? And that's a really, really hard problem. 10 to the 30 is no joke, right? I don't care who you are or how powerful your classical computer is. That's a very hard thing to go do. And this is a lot of the motivation behind the initial quantum computing push is if I have a quantum system that's highly entangled, it doesn't have to be very big or complex before it just becomes completely intractable to compute with a classical computer, right? And so you say, well, now I need a quantum computer to simulate quantum materials, right? But it turns out that's not what they're only good for. There's Shor's algorithm that has nothing to do with the quantum system, but it has an exponential speed up over the best known classical algorithms. But there's this caveat that Chris mentioned, which is, at any given time, the quantum state spans this full 2 to the n Hilbert space, and you need this 10 to the 30 complex amplitudes to describe it, but when you measure it, it collapses into a single state again. And so that's where you need to come up with these very clever algorithms that use kind of the fact that this phase allows quantum interference between these different probabilities, right? And you want to try and amplify the right answer and zero out all the wrong answers, and then you can actually, compute something potentially. The other bad news is qubits are really fragile, right? Because of this phase relation. Oh, I should mention, these complex amplitudes. We talked about analog computing in a couple talks at this conference. These are continuous variables. So even though this is a digital model of quantum computing, there's analog models of quantum computing. It's a digital model of quantum computing because you're using single and 2 qubit gates. But you have continuous variables, right? So it's kind of like analog computing in a way. And you might say, well, then it's impossible to do error correction, right? Because analog computing, it's really hard to do error correction. So it's really kind of an amazing result that you can do quantum error correction. But these continuous variables and this dephasing means you have really high error rates. So compared to classical computing, this is some 2008 IEEE paper. I love this title, Designing Reliable Systems with Unreliable Components. And I see 10 to the 28 operations per one error, and I'm like, that's unreliable. I'm pretty jealous. Because quantum technologies, the kind of current state of the art, is more like one error every 10 to the 3 2-qubit gates. And so, for this RSA Shor 4096, you need maybe 10 to the 12 2-qubit gates. So then for some of these big applications, you really do need some sort of error correction or very, very strong error mitigation. It also tells you that what's important for quantum computers is quite a bit different. There's a lot of times people just want to count qubits, or they want to talk about clock speeds. But the things that's most important tend to be these error rates and some other of these high quality qubit features, as opposed to just the number of qubits or the clock speed. So Chris showed a similar picture. I think these are these very beautiful ion traps. This is a 3D rendering, but we have some very nice photos as well. As you mentioned, this is kind of like this is in silicon. This is CMOS. This was made up in Plymouth, Minnesota, at Honeywell fabrication facility. But it's CMOS, but it's only passive at this point. It's just these boxes are just little electrodes. They have multi-layer metal underneath to route electrical signals, and you're just putting electrical signals on these electrodes to trap the ions in 3 dimensions above the surface of the trap. As we scale, we want to make more and more complex ion traps and start putting more functionality. So start putting photonics, start putting active electronics. You can even imagine active photonics to really enable scaling. And so our architecture, it's a little different than what they're doing currently at Duke for the most part. And it's based on this idea, and Chris mentioned it, this kind of quantum charge coupled device where you're physically moving the qubits around the ion trap and rearranging them. And it's actually an architecture. Chris was one of the first people to propose this, along with his, I think, postdoc advisor at the time, Dave Wineland at NIST Boulder. But the upshot is, we do have these perfectly identical qubits, right, of atoms. And then what you want to do is make the environment they see perfectly identical. And so we always have the same 4-ion crystal when we do our 2-qubit gates. And it's 4, not 2, because there's 2 ytterbium ions, which are used for the qubit, and 2 additional barium ions that we actually use for a sympathetic coolant. So as Chris mentioned, we're using laser cooling to actually cool our qubits. We can cool with lasers to much, much colder temperatures than any cryostat. And we use a different species because the laser cooling acts on the internal degrees of freedom of the atom. And so you want to store the quantum information in the ytterbium, and you do the cooling on the barium, and it sympathetically cools the ytterbium because they have shared motional modes in the trap. So this is our newest generation of machine that came out a couple years ago. We'll be launching yet a newer one this year. This kind of has this racetrack geometry, and you can see a video. These are individual atoms, right? So we're controlling individual atoms to this very exquisite precision. And this is kind of NASCAR mode where you're just doing turns all in one direction, but we can do much more complicated ion dances where we can arbitrarily disconnect and reconnect the ions to each other and do gating between any pair of 2 qubits. And then last year we upgraded from 32 qubits where we launched the machine to 56 qubits, which is an important number, and I'll get to that in a little bit. So I talked about the qubit quality, right, as being what really drives what you can do with current quantum computers. And I guess this reminds me of the graphs we saw this morning from Laura, but this one's just a simple 32 qubits. These are, circles are denoting the qubits, and every qubit's connected to every other qubit. In our case, it's not wires that's connecting them, it's this ion transport operations. And one kind of important aspect here is, for other qubit technologies or even different architectures and trapped ions, each one of these connections is unique and would require you to do a set of calibrations for that given connection. But since we're always operating with the same 4-ion crystal and we're always using these perfectly identical qubits, we don't have to calibrate the qubits, we calibrate the interaction zone. And for us, we can just have a handful of those. And so even though you have like 32 choose 2 potential qubit pairings here, you only have 4 sets of calibrations. And then some of the other qubit features. So we have this, what we call parameterized angle 2-qubit gate. So this is the entangling gate. We use kind of the ZZ phase gate. But you have this angle, and as Chris showed at pi over 2, it's a perfect entangler, but your algorithm doesn't always want that. And so we can directly encode this parameterized angle gate as opposed to having to do multiple kind of pi over 2s with single qubit rotations. And then it's very important both for near-term applications, but also for quantum error correction, to be able to measure your qubit in the middle of a circuit and then actually reuse that qubit. This is kind of how you do the quantum error correction syndrome, extraction, and so forth. So I'll talk just very briefly about benchmarks, right? So we have a full suite of benchmarks. It includes like component level benchmarks. This would be, say, single qubit randomized benchmarking to show you the errors in single qubits, 2 qubits. System level, which is kind of like a quantum volume test. This is something that was invented by IBM, but we use other people's benchmarks. And then application, where you're doing a full application and trying to benchmark your machine that way. And we tend to try and do all of these. And I think within quantum computing, there is a lot of times where people would launch systems without really much information at all. So we tried to really push for being the change we want to see in the world. And when we launched, say, the H2 system, we had an archive paper when we publicly announced it on the archive that same day. And it had this full list of benchmarks, right? Which went all the way from the component level down to the algorithmic level. And I think it is making some impact that people are putting more information out there. Chris kind of hinted at this. So one thing, when you have a quantum computer kind of over 50 qubits, that's where it's starting to become very, very hard to do full state vector simulation of those 50 qubits, right? You have this 2 to the 50 possible, dimensional Hilbert space. It becomes very hard to do full state vector analysis. And so you want to start showing a quantum computer can do something that the most powerful classical computers can't do, right? It's like a necessary but insufficient condition to get to useful applications. And so the first thing is just create random circuits and just essentially see how well the quantum computer versus the classical computer can kind of simulate a perfect quantum computer, right? So it's totally cheating, but it's the lowest hanging fruit. And like I said, you have to kind of check this milestone before you can go to other things. And so the idea is, you create some random quantum circuit. You're going to have 2 to the n possible outcomes, right, when you measure the state at the end. And any given quantum circuit, it's going to have some structure. And so there's going to be some outputs that are more probable and some that are less. And if you do a good job, if you do a bad job at random circuit sampling, you'll get ones that are less probable. If you do a good job, you get ones, I don't think the colors are showing up very well. You get kind of the higher output probability measurement outcomes, right? And so you can quantify this with this kind of cross-entropy benchmark. But then as Chris said, like, well, how do you actually prove that your quantum computer did what you thought it did, right? How do you do the verification if the classical computer can't give you the right answer? It's a very legitimate point. But one of the things we do is we actually mirror the circuit. So you can do a quantum circuit, and then halfway through, you basically mirror all the operations, so you get the same output state as as you had as an input state. So now it's a known output state. But then you can say, well, maybe I just undid all of these coherent errors. So in the middle, you actually do some randomized compiling and kind of change the basis that you're making the computation in, and then it becomes extremely unlikely that you would somehow accidentally undo all the errors from the first half of the circuit. And there's a bunch of details here. Then we show that mirror benchmarking kind of reproduces what you'd expect in the regime where you can compute the right answers. And then you kind of extend it into this regime where you can't. And in the end, we did a bunch of circuits and did a bunch of detailed analysis on how well classical supercomputers could simulate the system. And this is some cost and flops. And you kind of asymptote to this, what you have to do, a full state vector simulation of the machine. And then this is like some unlimited memory assumption, which is not realistic. And you put more realistic memory constraints, and all of a sudden, the problem continues to get harder as you grow the depth of the circuit. So in this like unlimited memory case, maybe it would take frontier minutes to do. In the more realistic case, it's a good approximation to never being able to do it, thousands of years or something. So a brief history of quantum advantage claims. This sums it up pretty well. You claim your quantum computer can do something that a classical computer can't, and all these otherwise very nice people come out and say very mean things about you in the form of archive papers showing how they simulated your quantum computer. I think in 2019, when Google made this announcement of the first kind of quantum advantage with random circuit sampling, people came and said, well, it's not quite as hard as you thought. Well, not nearly as hard as you thought. And it didn't quite stand up the test of time. But since then, they had an improved paper in 2023. We had one in 2024. They just had one a few months ago with their new Willow chip. And I think the bottom line is those are going to be much more difficult to kind of spoof with classical computers. We have a lot of caveats because this is how we talk. But we really believe that basically the classical computing algorithms are exploiting the fact that you had finite fidelity of your quantum computer, and that made it much easier to simulate this approximate solutions. But as you lower the error rate, you kind of hit a threshold where these tensor network methods and things just fail, and we think we're on the right side of that. And the thing is, once you get a big enough advantage with a quantum computer over a classical, since there's this exponential scaling for a lot of problems, like there is with this random circuit sampling problem, even with classical methods improving, you'll probably keep staying ahead once you have a big enough lead. And another thing to point out, this is kind of, so sorry I don't have the latest Willow result, that's out at 100 qubits, but this is actually showing kind of circuit fidelity estimates for the superconducting qubits versus the trapped ion qubits, and this is why Chris can say, these things are garbage and this is good, as only Chris can. And so there's this big gap in fidelity, right? And that gap's important because, the bigger this gap is between kind of what the classical supercomputer can do to emulate your quantum computer is and what your quantum computer can do, that's kind of the gap where you find the useful applications, right? And so we have to keep growing that gap. And so I'm not going to talk about chemistry. Chris mentioned I might talk about chemistry. Sorry, I'm not talking about chemistry, but I'll talk about some other stuff we're looking at, somewhat related to chemistry. I think solving the ground state energy of molecules is a great application. I think it looks pretty daunting for the near term. Some of the more lower hanging fruit might be looking at more chemical dynamics. That might be a better problem for near-term quantum computers. But here we're just thinking about, trying to do a physics problem, right? A real physics problem that you can't do on a classical computer, any classical computer, but maybe you can solve on a quantum computer. And it goes back to this idea of, all of a sudden I have 100 two-level quantum systems, and if they're highly entangled, it's impossible to kind of simulate it, right, with a classical computer. And so here you're looking at doing a Hamiltonian simulation, right? So you have some Hamiltonian that describes your quantum system, and you want to time evolve it, and you want to take these very small time steps and see how it thermalizes, let's say, and see what the properties are given some input state. And so you need very small time steps, which means these 2 qubit gates have to be very weak entanglers. But it turns out if there's very weak entanglement there, the classical methods do much better. Like it kind of improves that threshold of what errors they can deal with. And then over on this side, you have the kind of the easiest thing for the quantum computer, and the toughest thing for the classical computer relative to the quantum, which is these perfect entanglers, which is what you're doing in random circuit sampling. And then in the middle, you kind of have, these partial entanglers that are somewhere in between, and we kind of call these the Floquet circuits, and then you might be able to get to some interesting physics actually. So, one thing I'll say as we try and move from the left to the right, this is easier for the quantum computer, but it's a lot less useful. And then over there, it's like, okay, this is actually solving real physics problems, right? And so what you want to do is you want to have, as you lower this entangling angle, you want to actually have lower gate error on your quantum machine, and that's what we have with our parameterized angle 2 qubit gates. There is some offset. This offset becomes important as you try and do this Hamiltonian simulation, and there's ways that we can lower that, and I think that'll be important as we go forward. But then as you look at this, kind of the endpoints, you can think about what am I going to see in my physical model. So if I take infinitesimally small time steps, again, I'll see some dynamics, and then it'll thermalize, and you'll get some real properties of the physical system out. If I'm way over here on the perfect entangling side, you don't have this time invariance, and then you don't have energy conservation. And what happens is you basically quickly shoot to an infinite temperature, and you just get random states, and it's totally boring, right? And it doesn't really teach you anything. And so how do you transition as you go and make these steps kind of smaller and smaller, going from the right to the left? Then you get something that looks like this middle curve. And so you see some dynamics, and it equilibrates to some finite temperature. And then it tanks, right? It goes to this infinite temperature bath. But that happens at some time that's like exponential in the inverse time step. So you don't have to make these time steps too small before you can get interesting physics here. And then the delta you get here between this is just some value of some generic observable. That error is kind of related to 2 things. One's the error of the gates, and the other is the error induced by this finite Trotter step, right? The finite time step. But we kind of think that in both cases, those errors aren't nearly as bad as you might naively assume. And so the upshot is we really think, in the very near term, we can start showing interesting physics solutions that rival, classical supercomputers or even beat them. And I think we can do that on H2, but then on the Helios system, I think it'll be more of a slam dunk. So this is the system we'll be building this year. This will be the first time we have a commercial quantum computer with this junction transport. So it's just, instead of having this 1D or quasi-1D ion trap, you actually have kind of an intersection of these streets. It's not as trivial to do as you might think in these ion traps, but it just allows for faster sorting, faster operations, lower memory errors because operations are going faster, and then we're switching to barium qubits because we think it will provide lower error rates. So the upshot is we'll get more qubits, they'll still be fully connected, there'll be lower errors, faster operations, and I think we'll really see even more separation between this machine and what you can simulate classically. So here's kind of the roadmap. So we released this H1 system. It's this very linear trap design in 2020. It started it with 10 qubits. We've upgraded it to 20. The 2 qubit gator is kind of 10 to the minus 3. Released the H2 system. It's now up to 56 qubits. This year we'll be at Helios on order 100 qubits. And then we moved to more of a modular, more tileable sort of design where you have many of these junctions, kind of a junction array for the ion trap. And then you see this kind of large jump in scaling as we go from this machine we call Sol to the next one called Apollo. It's kind of coming for a couple reasons. One is, we continue to scale, and we're scaling, maybe doubling the qubit count every year and a half or so, I think, historically. But we're also lowering the error rate as we go, and we have been steadily since we released our first system in 2020. This system started off much worse than 1 to the minus 3. But once we get to the kind of the Sol and Apollo level, you start to see, like, once you're down this low 10 to the minus 4s, you get kind of diminishing returns on how, it becomes harder to lower the error rates, and you also get diminishing returns on like QEC overheads. And so the right thing to do is at that level is to just focus on scaling, right? So now you're not trying to scale and improve the qubit quality, you're just focused on scaling, and then we should see faster scaling there. How are we doing on time? I don't have too much more. I just want to talk a little bit about quantum error correction. I think Chris and I probably slightly disagree on the need for quantum error correction. I do agree that looking at error mitigation techniques is very important, especially in the near term. But eventually you do want to get to this full-scale quantum error correction. So, dealing with the fact that you're only getting 1,000 operations before you have an error is a problem. So you kind of encode qubits into many qubits, and these are called logical qubits. So this is similar to classical error correction. You just have redundancy, right? So there's the repetition code to guard against a bit flip error. A 0 can randomly turn into a 1, but if you encode that 0 into 3 zeros and the 1 into 3 ones, a single error, you just do a majority vote, right? And if you want to correct for 2 errors, then you add more bits to your repetition code. But quantum's a little harder, right? Hide the pain, Harold there is telling you that. So you don't just have bit flip errors, right? We have these continuous variables. It turns out there's this kind of digitization of quantum errors where you have bit flip and phase flip errors, but it's not an infinite number of errors, right? You have this measurement collapse. You have this no cloning theorem, so you can't just make copies of quantum states. And there's this kind of Easton-Knill theory that tells you in these quantum error correction codes, it's actually very hard to get a universal gate set, but there are ways around it. So it's kind of amazing that this is possible even, and the theoretical work that's happened over the last couple of decades has been really impressive. And now we're finally realizing this theoretical thing on physical systems. And so this is work we did with Microsoft last year, where we're doing, we're not just creating logical qubits and encoding them now and looking at memory errors, for instance. We're actually doing gates between multiple logical qubits. And we're actually starting to see improvements over the physical error rates. So when you first do this, you're having to do a lot more physical gates to encode and to do operations. And so if your error rates are not low enough, you're not beyond this threshold and you're actually making things worse. So to actually show that you're making things better for the first time is, it's a big milestone, I would say, in the field. And so here we have some data, physical error rates. It's a distance 4 code, which means you can correct one error and detect a second error. So we have both data where we're just doing the error correction, and then we also have the throw out the ones that you detect a second error on, and you get even lower error rates, right? And then we can show that we can do this multiple rounds. There's two different physical comparisons here. It's a little subtle, but this is the physical data, and this is the logical data. And you can see it stays below, but it's just kind of like it has some offset. What you really want to see is like better slopes. We're starting to see better slopes, but that data will come out soon. Spoiler alert. And then, I always like to discuss in all my talks this Oak Ridge National Lab program where they buy a subscription to different quantum computers, and then academic researchers can actually go online and apply to get the resources. This is very important for not only like the government kind of helping quantum computing companies show some revenue, but also increasing this ecosystem of people designing quantum algorithms, right? I think we talked a little bit earlier today about, there's not a lot of these quantum algorithms out. They're really hard to come up with. Like, it's very subtle. People don't really think quantum mechanically, right? All of our interactions are these classical interactions within our day-to-day lives. So just getting more people looking at quantum algorithms is important. And I had a couple people mention, like, what about the software side? So I'm very hardware focused, just like Chris. I'm an experimental physicist. I think mostly about the hardware side. Our company is very full stack. So we have, Chris mentioned chemistry. We have a whole chemistry suite. We have, all these different algorithm libraries. We develop our own algorithms, but we're also kind of software agnostic, where people can run their own algorithms on our machines, but we're also kind of hardware agnostic, where we have this software stack, and you can go to other backends that are not just our machines. There's kind of middleware, kind of circuit compiler, optimization tools, tools that help you write better quantum algorithms, the quantum error correction level, and then the hardware level. And with that, I will end and take any questions.
Excellent. Thank you very much.